Hey everyone, thanks for coming to this afternoon session where we'll be talking about visual effects and animation rendering on GCP. My name is Todd Prives and I'm a product manager here at Google, and I focus on solutions for the media and entertainment vertical. So during this particular session, we've got some Oscar caliber customers who are going to share with you their experience of using GCP to render imagery that's high quality, cost effective, helps them deliver projects on time, and really most importantly, as far as visual effects and animation goes, it serves the creative purpose of the story. So I'll start by giving you a brief overview, talk a little bit more about what rendering is at a high level. We'll look at some of the things that GCP has done to enable studios to achieve really great high-scale rendering. And then we'll hear from Monique Bradshaw. Monique's VP of Business Development and Operations at Conductor IO. They're a cloud rendering platform running on GCP, and their customer, Atomic Fiction, just put through several million hours of rendering on GCP on the film The Walk. And this is a film from Oscar winner Robert Zemeckis, and the film itself was shortlisted for the Oscar Bake Off for Best Visual Effects this year. After Monique, we'll hear from Brennan Chapman. He's the head of pipeline at Moonbot Studios. They themselves an Oscar-winning studio in Shreveport, Louisiana. And Brennan's going to go ahead and share his experience of using GCP to set up a hybrid environment for rendering, where he's been able to use his on-premise resources and then burst to GCP for excess capacity and really demanding jobs. So at a high level, what is rendering? Well, there's several different variations, but really for the purpose of media entertainment and animation, it comes down to this. Taking a model inside of a 3D application that's been built by an artist and taking all of the data associated with that model. So that could be textures, that could be geometry, that could be assets, that could be animation, that could be lighting. Imagine to accurately light this, you could need to set up thousands of points of light. So it's taking all of this data and number crunching this to give you a final, fully realized, photorealistic output such as this. So this is a single frame here, and to run this render on a 32-core machine takes about an hour, just to give you a little bit of context of what this one particular rendering job is. But keep in mind the scale of most projects. What I'm showing you here is one frame. So to get 1 second of animation for a film or television project, you're talking about 24 frames. So right there, you're looking at 24 hours on a 32-core machine to render 1 second of animation. And then you want to go do 10 seconds of animation, a minute of animation, 60 minutes, 90 minutes. So by the time you're at a full animated feature film, the numbers are really astounding. And in this particular case, it's an hour render. But in the case of The Good Dinosaur, this is Pixar's last movie. I actually just saw these stats 2 days ago. This was a 48-hour render a frame project. So this is something like 175,000 frames, each one taking nearly 2 days of render time on a high core count machine. So imagine when you're delivering a film of this scale and of this scope, you're looking at renders in the hundreds of millions of core hours. So it's very daunting, it's very demanding, and these numbers are increasing year over year. Audience expectations are getting higher and greater, and the demands and the vision of the director is also increasing in scope. It's also important to note that rendering isn't just a really important use case when you're talking about big animated feature films or movies with superheroes or spaceships or dinosaurs. It's everywhere. So rendering is really ubiquitous in what you're seeing on television today, at the cinema, or whatever you're watching on your mobile device. And as Monique Bradshaw is going to talk about in greater detail, The Walk is a perfect example of this. So this is a character-driven piece. It tells the story of a Frenchman, Philippe Petit, who put a high wire between the two twin towers of New York and walked across it. So there's no spaceships here, there are no monsters, but in order to create this environment, this photoreal world, to help sell the vision of the story, the visual effects studio Atomic Fiction that worked on this had to digitally recreate massive parts of New York and render this. And for a story where there's nothing obvious as a visual effect, you're still looking at over 9 million core hours needed to make this movie. So it's really important to note that anytime you're watching something on TV, at cinema, on your mobile device, it's very likely that there was a significant amount of rendering required to produce that output, whether or not you realize it. And so what are the challenges associated with rendering? Well, obviously, as we've demonstrated, it's incredibly computationally intensive, and it's also very bursty. Both Monique and Brennan will attribute to the fact that you're working on a project sometimes for months at a time. Maybe your on-premise capacity is at maximum utilization, and there are always last-minute changes that come in. The director has new things they want to see, the script's been revised. So you can never have enough capacity, especially in that month or two before final delivery of a project. There's always a need for more, always a need for more. So bursty workloads are really something you see whether you're working on a small commercial and you've got 5 or 6 projects coming in at the last minute, or a large feature film. Another advantage or a need to have centralized compute is in multi-site locations. We've really seen in the last 5 to 7 years studios opening up worldwide locations. So it's not just one studio working on a project for 10 and 12 hours a day and going home, but instead they'll work on that shot, let's say at the headquarters in London. That shot will get passed off to the team in Montreal working on it. They'll work another 8 to 10 hours, and it'll get passed off to the satellite office in Singapore. So we're seeing more and more of a 24-hour dynamic workload, even among smaller studios. So the need for having rendering scalable compute resources is really critical. And how does GCP fit into all of this? Well, our machine capacity obviously is a critical part to all of this. Right? GCP is the network that runs Google. So what we serve ads and search and YouTube, all of this was built at Google scale. So for us to have a studio come to us and need to provision 20, 30, 40, 50,000 cores in a matter of minutes is no problem. And you contrast that with a studio having to go out and find the physical space and bring in all the machines and set up their networking. Oftentimes, if they only need it for a week or two of burst capacity, it's really not feasible. So the scalability we offer is really unparalleled in the industry. I think our pricing model in particular is fantastic for bursty rendering workloads. You only pay by the minute after a 10-minute minimum. So this allows you to really scale your workload in parallel. Going back to the example I gave before, the police car. So let's say that's 1 hour to render, and I have to render 1 second of animation. So that's 24 frames. So what I would do on GCP is spin up 24 VMs concurrently and assign 1 frame to each of those. So there's no longer the concept of having to wait for a job to queue behind a limited available number of machines, but the job is done as fast as possible, and that's returned back to your artists so they can continue to iterate and revise work in a manner faster than ever. And when it comes down to running an animation or a visual effects studio on a day-to-day basis, your highest costs are really that of your human capital. You're paying these artists several $100s a day to work on these shots. And if you think about it, if they're sitting there waiting for these renders to be returned while they're in a limited on-premise environment, they're not working when they should be. They're not working at full capacity. So not only are you taking into account the infrastructure spend, but you're also wasting a lot of this human capital. And then specific to the visual effects and animation and media entertainment industry, we've done a lot of things at GCP that really differentiate us from any of the competition out there. Studio-specific security is a huge issue in our industry. Often cases you're talking about billion-dollar, tentpole blockbuster franchises. So if any of that data was to leak ahead of time, the Hollywood production studios could be looking at hundreds of millions of dollars of losses. So there's an incredible amount of concern over putting your data in the cloud when it comes to this sensitive, pre-release theatrical content. So what we've done at GCP is actually work directly with the Hollywood production studios, educating them around our security and our compliance. And in several cases, we've actually undergone studio-specific audits of GCP that have awarded us a Tier 1 certification, allowing our customers to put the most sensitive, pre-release theatrical content on our cloud for rendering workloads. We've also built scalable solutions for all types of studios. So if you're a small studio and you want to do rendering on GCP, we have a product called Zinc Render. And this is a turnkey solution, all-inclusive, no coding needed, and it's literally a plugin you install inside of your host application, and you can access tens of thousands of GCP cores to render your project instantaneously. And for larger studios with more custom pipelines, we have a dedicated solutions architecture guide that's been written for us in conjunction with a technical director at one of the leading studios in North America, a studio that's been using GCP for well over a year and a half to do their rendering. And this is a full breakdown, a step-by-step guide of how to integrate your existing on-premise infrastructure and tie that to GCP for rendering workloads. And really the backbone of all of this is our ISV relationships. So our industry, no matter if you're a 5-person shop or you're a 1,500-person shop, the core stack is the same. Everyone is working with the same standard commercial tools. They might have their own additional software that they've written on top of that, but tools like Nuke from the Foundry, V-Ray from Chaos Group, and RenderMan from Pixar are the foundation of all rendering workloads in media and entertainment. So we've worked very closely with the top ISVs in the industry. And if you look at this list here, there's not a single Oscar-winning film over the last 15 years that has not used some or all of this software here. So we're working very closely with these ISVs to enable a scalable deployment on GCP that's concurrent to the scalable model we offer with our billing. And the results so far have been awesome. We've seen hundreds of millions of core hours now put through GCP across feature film, commercial advertising, episodic television, VR content, live-action cinematic rides, and animated projects, just to name a few. So we're excited to continue to see this uptake of our product. And I'll go ahead and turn over now Monique Bradshaw. Again, Monique is VP of Business Development and Operations at ConductorIO, and she's going to share the story of atomic fiction. Monique.
Thanks, Todd. As Todd said, I'm Monique Bradshaw from ConductorIO. And ConductorIO is a company that provides cloud computing as a service. We focus on the image rendering needs of the media and entertainment space. And ConductorIO provided the cloud rendering capabilities for atomic fiction for the work that they did on the recent movie The Walk. As Todd said, the movie The Walk tells the story of the true story of wire walker Philippe Petit, who strung a wire illegally between the two towers of the World Trade Center and walked across it without any safety gear at all. And today I'm here to share with you the story of how cloud computing played a critical role in atomic fiction's ability to recreate the Twin Towers and the New York cityscape of 1974 for the movie. But before I tell you about the movie The Walk, I'm going to tell you a little bit more about how compute resources are used to create visual effects for film. Now, Todd touched on this a little bit, but I wanted to go in a little bit more detail because it can get pretty complicated. So in the beginning of a shot's life, an artist works with a lightweight wireframe representation of the scene, basically like the top image there. Now, the relative simplicity of this scene makes it quick to interact with locally, so a team of artists can work within interactive graphics programs to create recipes for how cameras move, how surfaces are textured, and how lighting falls on objects. Now, once that recipe is defined, it needs to be baked. This process of calculating how light is received by, reflects off of millions of surfaces is called rendering. And the results of this process can be seen in the bottom image. Now, in a film, a single second of footage is typically made up of 24 images or frames. It's not unusual for a single iteration of a single frame to take between 5 and 10 hours, sometimes even more, to render on a single multi-core machine. So, given that, it's easy to multiply that out and see how a single iteration of a single second of film can actually require thousands of hours of compute time. So, to understand how important cloud resources were to the creation of the effects in The Walk, let me talk a little bit about the hurdles that had to be overcome for this. As I mentioned, ConductorIO worked with Atomic Fiction, and they were the visual effects company that was charged with putting the audiences 1,400 feet above New York for the climax of the film. The first challenge they had to overcome was creating the environment. The towers themselves had to be built perfectly down to every last nut and bolt, and artists then spent months introducing imperfections to make them look hand-built. The activity in the streets below, from the cars to the people to the flocks of birds, the moving atmosphere were all created from scratch. The scenery below was created too, with spinning fans and rooftop HVAC systems, rain gutters on buildings, hot dog stands in the streets, and changing stoplights to make the city feel alive. Every conceivable camera angle had to be accommodated, and that meant a number of lighting scenarios, everything from nighttime to early morning to a blustery overcast day to a sunny fall afternoon. All of that flexibility and complexity meant that a massive amount of compute time would be required. For The Walk, a single iteration of one frame required 83 gigabytes of input data and took over 7 hours to render on a 16-core instance. If you multiply that out, and given the nature of production deadlines, it meant that the artists at Atomic Fiction would need the ability to access over 15,000 cores of compute power simultaneously for sustained periods of time. The second challenge that Atomic Fiction had to face was the tight budget that they had to create these effects. Now, for a medium-sized company, To acquire that amount of compute infrastructure locally would require leasing or renting a large amount of computer systems, as well as sourcing co-location facility, the appropriate technical support, and all of that would add up to a financial obstacle that would have blown the budget for them. Additionally, visual effects companies don't realize any profit till the end of a project. So it's incredibly important for Atomic Fiction that they could get up and running with as little overhead as possible. This is an important graph. It illustrates the financial challenges typical of rendering needs in the visual effects industry. So as an example of a medium-sized visual effects studio, the jagged blue line represents Atomic Fiction's actual work profile and relevant spend for compute resources. The red line represents typical resource profile for a growing visual effects company that's investing in on-premises resources. In this traditional environment, resources are acquired to try to cater to the peak need. The time, effort, and money required to implement those additional hardware means that the resource profiles plateau around the last peak need, and they can't adjust downward to match the actual render workload at given times. So what you can see here is that the pink shaded area is where on-site resources are over-provisioned for the actual workload, and that represents wasted investment. The blue shaded area is where on-site resources were under-provisioned for workload requirements, and that represents a negative impact to artist productivity. So as you can see, the spiky nature of typical content creation workload results in companies cycling between the cost of limited computing power negatively impacting the productivity of their artists and too much dead weight being carried during downtimes. So the solution to these challenges of complexity, cost, and challenging work profiles was to utilize the flexible capacity of the cloud. And that's where ConductorIO comes in. So Atomic Fiction utilized Conductor's cloud rendering platform to manage its cloud computing needs for the film. Now, the benefits of cloud computing can really be summed up in one word: scale. If you take a look at this simple table, you can get a very clear contrast in two styles of managing work. In the first column, you see 1,000 tasks spread across 50 instances that result in a total turnaround time of 10 hours. In the second column, you see the same number of tasks spread across 1,000 instances, resulting in a turnaround time of only half an hour. Now, as you can see, there are good reasons for each example of resource allowance, but one of the biggest benefits of elastic scaling is the ability to scale up rapidly as the need demands, allowing artists to iterate faster. That improves productivity and creative quality by limiting the amount of time that artists have to wait around to see the outcome of their work. And it allows them to be creative and iterate faster in the same amount of calendar time. Large peak capacity and rapid downscaling lets teams postpone their render needs until later in the schedule, and that's creatively and financially beneficial. The on-demand scalability afforded by GCP allows companies to maintain a direct relationship between project cost and revenue. No longer does a studio's revenue need to cover unused but costly infrastructure. In addition, these days, data and analytics are critical aspects of pretty much any company. The scale of data collection and analysis of large amounts of metadata that's enabled by leveraging cloud architecture also allows for better cost management and streamlining of workflows. So, Conductor is written on top of the Google Cloud Platform, and it provides functionality critical to meeting the needs of a demanding visual effects production. So, for us, there were a number of key factors that we needed to evaluate in choosing to use Google. The big one from a business perspective is the ability to do per-minute billing, which Google enables. When we're providing a service to an industry where workloads are often broken down into tasks that require fractions of hours of compute time, the ability to offer true pay-per-use is a critical aspect and a critical part of our value proposition. Now, obviously, Google's a global company, and that global presence is incredibly important for us. Single customers that we have may have studios in locations as diverse as Europe, North America, and India. And being able to provide a standardized service that they can interact with from any location in the same way is very important. Also, Having access to the vast engineering talent at Google to help us work through architecture optimization or resolve issues gives us the confidence to provide a service to businesses where uptime is incredibly important. Now, one of the holy grails for the visual effects industry is really being able to mine data for bidding accuracy and thorough render cost analysis. And accurately predicting the time and cost for a given render job is also critical. Now, to do that at scale where we have thousands or millions of concurrent tasks generating data constantly, we needed a powerful database option. And for us, that's Bigtable. With Bigtable, it's huge, it's extensible, and it's incredibly responsive. And when we have huge numbers of jobs running at the same time through Conductor, we can then use BigQuery to access that data and present it quickly to our customers, providing them real-time information about how their work is going. Finally, Google App Engine offers us a ton of configurability out of the box, which is really important for a small company to get up and running quickly. And it's an important capability for our team because it allows us to focus on implementing our key roadmap features rather than worrying about our application architecture. All right, so to talk a little bit about Conductor architecture. One of the most important things for us was to have as little impact on the artist workflow as possible. So we created plugins that fit into the most commonly used software for artists, and then that is installed in the artist's local machine. Other than that, the artist workflow is pretty much unchanged. They work as they always have. They save their data to the right place in the local network, and that's it. When the artist is ready to render, they pull up the installed Conductor plugin, enter a few bits of parameters, things like choosing the instance type, setting up the frame range, and then they just hit submit. The plugin then sends those job parameters to the Conductor application, which serves as the brain of the Conductor service. The application is hosted in Google App Engine, and there initiates a number of key functions. So the app uploads dependent files and data, including files, scripts, and environment variables, via an uploader daemon from the local file system to the cloud, where we also do a deduplication process to make sure that we're using the storage as effectively as possible. The data is initially stored in GCS, and then specific instances are spun up to sync data from GCS to a Gluster NFS share. And we scale up at 100 render instances per Gluster instance in order to meet our I/O needs. Now, the Conductor app also determines the required number of render instances and spins up the right number from Google Compute Engine, scaling up quickly, reliably, and massively. We run a Docker container that's customized for our execution environment. Using Docker allows us to potentially accept custom images from customers, and that's a major benefit for highly customized studios. The render instances read the necessary input files from the Gluster share. Once all the components are running and active, the the Conductor app manages the rendering process from start to finish, including licensing, queuing, error handling, and metrics collection. The web UI, also hosted from Google App Engine, allows users to control and monitor the render jobs from wherever they are. Data store is used to store the output, to store state and operations. Job metrics are stored in BigQuery for easy access, and also made available via the web dashboards. Once a job completes, the output is stored in GCS and Gluster NFS for future ease of use. The data is also downloaded to a local path specified at job submission, so the artists have that in their local environment again. If there are no further jobs requiring that same instance configuration, then the Conductor app shuts down any unneeded instances. So, what does that really mean and result in when it's put into use? Let's take a quick look at a quick 2-minute clip of some of the effects that were for the walk that were generated using Conductor. that gives you an idea of the real complexity that goes into making a movie. And also it tells you that the best effects are the ones that you don't even know are there. So here's the final breakdown for cloud computing that went into creating those effects. Over 9 million core hours were used to create about 30 minutes of film. The final portion of the film was all done through Conductor. And of those 9 million hours, almost 3 million of them were in the last month alone. It gives you amazing evidence of the power and flexibility of scalability. Now, all of that equated to a peak total of over 15,000 concurrent cores running in Google Cloud for sustained periods of time. Another major benefit of the distributed nature of cloud computing is how accessible it is to people all over the world. For the portions of this movie worked on by Atomic Fiction, 75 artists collaborated from 2 different locations, the Bay Area and Montreal, Canada, without any change to workflow or additional management overhead. Now, as you can see, in order to accommodate the peak render load, we estimate that it would have cost Atomic Fiction about $1.5 million to procure the necessary local infrastructure. By using Conductor and the power of cloud computing, Atomic Fiction realized a cost of about 50% just on render infrastructure alone. Now, as impressive as all of those numbers are, for me, this quote really captures the power and the promise of cloud architecture. This is what we have the ability to do when we are able to leverage the capabilities and flexibility of the cloud. We have the ability to fundamentally change the way an industry works. Thank you very much.
Thanks for that, Monique. Some really great insight onto how they built their platform using GCP and some of the amazing photoreal visual effects work that they completed. So now we'll hear from Brennan Chapman. Brennan, again, the head of pipeline at Oscar-winning Moonbot Studios.
Thanks, Todd. Hi, I'm Brennan Chapman, head of pipeline at Moonbot Studios. Moonbot is based out of Shreveport, Louisiana. We have about 50 people on staff. We've been honored with quite a few different awards. A couple of projects you might recognize us from include the fantastic flying books of Mr. Morris Lesmore, The Scarecrow, as well as the Numberlies. These take multiple forms, including short films, apps, games, and even printed books. We pride ourselves as being a multi-platform storytelling studio, and we use whatever medium that we see best fit to tell our stories. A story I'd like to share with you today is called Taking Flight, and it's based on the life and heritage of Antonio Passon, the inventor of the radio flyer wagon. This short was rendered in part by Google Cloud.
You know, that wagon used to be your dad's. I guess your dad didn't tell you about the aliens.
Have you guys enjoyed that? So, that story was great, and we used a lot of cloud rendering on it. But the question is, why use cloud rendering at Moonbot? What is the benefit we get? And we've sort of touched on it a little bit. But just to state it from an exact Moonbot perspective, it increases our creative freedom, which is our golden ticket for Moonbot. It allows our artists to be more creative. It limits them from the restraints of the fixed capacity of a local render farm to be able to scale and accommodate any creative goal. And thus, because of that, we're able to meet our deadlines and not go past them, which is huge. And also, it helps us to save money. As they've stated, the rendering is a lot of burst workflow. And if we don't have to buy a local compute farm that scales to the peak times and we underutilize the capacity at other times, we save a lot of money. Similar to Monique's graph, here's a graph of last year we had about 3 projects that we were rendering. They were all sort of going on at the same time, including this project we just showed you, Taking Flight. And you can see 3 main things with this graph. One, you can see that there's these high peak times. There's times when we have enormous amount of renders. And by the way, this is a graph of the amount of hours each artist has submitted per day to the farm. The second thing you can see is there's times where we hardly use anything, maybe none at all. And the third thing you see is there's this orange line that we sort of target at Moonbot, and that's the sort of medium, the stuff that we use all the time. And our goal is to sort of have local compute capacity for that median line. Anything above that, we want to push to the cloud, because that's more cost effective for us. But anything below that, we'll render locally at Moonbot. So our rendering goals for implementation of Moonbot was we wanted it to be easy to use, we wanted local and cloud, so we wanted a hybrid approach, and we only wanted to use cloud when needed. We didn't want to treat cloud the way we do local nodes, where we basically just spin up 50 nodes that just sit there in the cloud. We wanted to only spin up nodes when we're using them, and sort of be smart about how that works. So there's two render farm strategies that we sort of see. There's, if we do everything in the cloud, you get sort of the render everything as soon as possible strategy. And that's because if you rent one node for 100 hours, you're paying the same cost in the cloud as renting 100 nodes for 1 hour. So if it's cost the same, why not render it faster? So that's great, so that's cloud only. But with a hybrid farm, you sort of get a different approach. You have this local compute capacity, and you get the best cost and savings when you fully utilize the local compute capacity, and anything extra you push to the cloud. But with that, you need a time component. You need sort of a deadline for each of your renders to be able to calculate, am I fully using my local farm? And once that's done, you push it to the cloud. So to do that, we present our artists with this dialogue sort of when they submit stuff to the farm. And the first option just asks them, when do you need this by? And they can set whatever time factor they want. It defaults to the next morning, because a lot of times they submit before they leave for the day. But this gives us our time factor to be able to know when is a render being completed by, and if we have time, let's render it on the local farm, and if not, we'll render it in the cloud. So great, so why did we choose Google Cloud to do this? Three main things. They had great support. So talking with them originally, they've helped us figure a lot of stuff and set up our pipeline to easily support this. They even suggested the second option of Avir as our storage vendor, and I'll get into that in 1 minute. And also they have per minute billing, which is huge for us. We only pay for pretty much exactly what we use. We're not paying for hour time slots that we might not use the full capacity of. So implementing the cloud rendering into our pipeline, we sort of face three main challenges. And I'd like to share with you some details with those. First is storage. How do we transfer our files to the cloud to be able to render with them? So here's what we need to transfer. We need to transfer 3D scene files and textures, and then we need to download the rendered frames and maybe logs back from them. We're also in Shreveport. We don't have the fastest internet available. We're sort of limited to this 100 megabit per second connection. So we have to be smart about what we're uploading and when we're uploading it. So there's two ways that we saw that we could sort of attack this problem. The first way is by writing sort of custom scripts targeted at each application. So how does the application load in data? And we have to isolate all that, maybe parse the scene files or something like that. And then whenever you render it out, we have to target and find what it rendered and transfer those back locally. But this is done very individual application specific. So we also, through Google's help, we figured out there's another solution called Avir. And this solution acts as like a cache to your file system. And because it happens at the file system level, it can be sort of a one-size-fits-all approach. So let's look more at that. So here's sort of a graph of how our infrastructure is set up. We have an Avir cache node that sort of sits in the cloud, and we have our core filer that sits on site. And the Avir will automatically upload data as it's requested to the cloud. And the cloud keeps this cache that can be then distributed to all the render nodes. The render nodes connect into the Avir and just ask for stuff. It doesn't have it, it uploads it from the core filer. If it already has it, it just serves it out of the cache. So the way this works is it mounts via NFS, which is the same way our local storage handles, which creates this nice uniformity between our local cloud and our Google Cloud. Makes it nice and easy. It also auto-uploads dependent files, since you're doing this just at a file system level. And also supports partial file transfer. So if you only need like the top head of your file, and you don't need to read the full thing, the Avir is smart enough to only transfer that part of the file. So the other challenge is how do we set up render nodes? How do we, preferably have a uniformity between how we have local nodes set up and the cloud nodes? And we came up with this workflow. We take sort of a base OS, we use CentOS in our case in the cloud, and we run our configuration management tool. We use Ansible and Moonbot to configure our local nodes, and then we can just run that the same thing again in Google Cloud on the base OS to get all the software and configuration and everything installed in a VM. We then bake that to an image in Google Cloud, plug it into an instance template and an instance group to be able to spawn up pools of those nodes. There's two types of instance types that we look at in Moonbot. There's the on-demand and preemptible nodes. Our goal at Moonbot is to try to take advantage of the preemptible nodes because they're less than half the cost. But they come with two side effects. Their availability is not guaranteed, and they also refresh after every 24 hours. The benefit, though, is the render farms are capable of handling fault tolerances to a degree like if a frame fails, it'll automatically be retried. So that's, by nature, as long as the preemptible instances aren't too wildly unavailable, we can take advantage of this preemptible instances and take advantage of the cost savings. And we use instance groups to manage the pools of instances. This is especially useful when you have preemptible instances because their availability is not guaranteed and sometimes they'll go away. The instance groups will automatically manage adding them back if they ever become available again. So we don't have to write all the code to handle that. We're also able to start and stop these pools of instances, and we sort of see a startup time of about 3 minutes to get everything running. So I can go into the instance group, say I need 50 nodes or 100 nodes, and 3 minutes later, they're on my farm rendering and doing the work. Instance performance was interesting too. We found that not all instances in Google Cloud are the same. Be careful if you're doing this, because we found that Haswell nodes were about 20% faster than the Ivy Bridge nodes, even though they might have a lower clock speed for our specific rendering applications. And with that, we sort of saw an 80% performance match with cloud nodes compared to local nodes. So it is slower, but the benefit is we can have a whole lot more of them. So the last challenge we really face is how to forecast renders. So if we want to do this hybrid approach, how do we really get that data to be able to know when to submit to the cloud? So what we need to compute is some type of total number of the pending render hours, and then from that, maybe we get the delayed render hours at sort of a specific point in time. So the way that we do this is an artist submits their job to the farm using the dialog like you saw earlier, and we split it off into 2 main groups. We have sort of preview frames and other frames. So what that means is you might have a shot that's about 1,000 frames long. You would take the first, maybe middle, and last, and you would render those with the highest priority first, maybe on your local farm, just whatever gets it done fastest. Then you take the time that it took to render those frames and use that to estimate the time it's going to take to render all of the other frames. We do this for each of the jobs that are submitted to our farm, and we end up with a total count of the pending render hours. We then use benchmarks of our local nodes to be able to see how much local capacity we'll have in a certain amount of time. And then we can get a benchmark of how many delayed hours there are in the cloud. We can use benchmarks of our cloud nodes to then get an exact count of how many cloud nodes we'll need to add for any time and to complete our renders by their deadlines. So great. So that's most of what we do at Moonbot to get everything on cloud rendering, and we end up with these 3 main benefits. We get creative freedom, we're more flexible, we can scale on demand, removes constraints on scheduling, which is huge. I can't tell you how many times I've had to rebudget based on schedule shifting, but the cloud enables that to be much more flexible. It saves time, we get faster rendering, simplified budget and planning, and increased flexibility. We pay as we go, we don't have to have this capital expenditure up front, and enables us to succeed as a company at Moonbot. So, thank you, and finish it up with Todd.
Thank you. Thanks everyone for coming to our session and hearing from our 2 great presenters on how GCP has really enabled them to dynamically scale their businesses in a manner that's cost effective and really most importantly gives them a lot of creative freedom. So thanks again, and we'll see you all tonight at GCP After Next, after dark.